So the first question, what was the plate strength during rifting? We know that massive volcanism happened throughout the Earth's history and formed large igneous provinces, mostly along plate boundaries, assisting the breakup of continents. For example, the Central Atlantic Magmatic Province, or CAMP, happened at the Triassic-Jurassic boundary about 200 million years ago, contributed to the breakup of supercontinent Pangaea and the formation of Central Atlantic Ocean. As we all know, the foundation of building at Lamont, the Palisades Seal, are part of CAMP. During the volcanic rifting process, an upwelling mantle plume impinges at the bottom of the plate, bringing in great amount of heat that generates voluminous melt that can erupt to the surface, like this magma fountain up to tens of meters high erupted in 2014 on Iceland. So to address the question, what was the plate strength to allow continent to rift apart? We look at the seaward dipping reflectors at volcanic rifting margins. They deposited globally and indicated by these red curves. So what are SDRs? Let's take South Atlantic as an example. Here's a cartoon showing a rifting margin, and SDR are deposited and seismically imaged massive lava flows deposited near the continent-ocean transition zone. And zooming in, we can see oceanic crust on the left, continental crust on the right, and these seismically imaged reflectors that dip toward the ocean. That's where the name seaward dipping comes from. In the next few slides, I will show how do SDRs provide unprecedented information to look into the historical plate strength. Here's a depth-converted multi-channel seismic profile offshore Argentina, South Atlantic. At the continent-ocean transition zone, we see these reflectors that dip toward the ocean, sitting beneath 4 kilometers of post-rift sediments. They usually have a concave upward shape, and each wedge thickened at depth. The SDR wedges generally has a spatial domain of tens of kilometers across, up to thousands of kilometers along strike, and several kilometers thick, resulting in a total volume up to 1 million cubic kilometers, similar to that to LIPs. And so how are SDR formed? Well, drilling offshore Norway indicate there are thin layers of sediment interbedded within thick piles of lava. Bowerson and Walker first proposed crustal drift and lava loading for producing the 2D lava flows on Iceland. Here's the rifting center, and AA prime shows these 2D lava flows dipping toward the rifting center. But how do we relate the plate strength to these bending lava flows? The research approach is that because the plate strength controls the SDR geometry, and so the geometry can reduce the plate strength. And basically, based on thin elastic plate theory, with the same loads on the left, the weak plate with low elastic thickness will have more bending, whereas strong plate with high elastic thickness will have less bending. And Roger develops the crustal drift and dike loads idea and first quantitatively describe the physical relationship between magmatic loads, plate strength, and SDR geometry. When a fluid dike open at the rifting center, we assume it has a density around 2800, similar to that of lithosphere, or similar to the country rock. And as it solidifies, it will load the plate downwards and cause the bending. Magma lava flows further loads the surface downwards. And repetitively, as the old dikes move off axis, new dikes keeps loading the surface downward. It can cause these bent lava flows that looks like the observation. In order to tell the plate strength, we need observables to link SDR geometry to that. And based on the math derivation, identify 3 observables of SDRs. The first observable is XF, which is the horizontal distance between the most band reflector and the tip of the flat reflector. It's proportional to TE to the power of 3/4. T is the elastic thickness. And the second observable is gamma, which is the ratio between the total thickness of SDR and the tangent of the dip angle at this point, which is also proportional T to the power of 3/4. When this part of the data is not available, we need a third observable, which is phi. As you can see, phi is almost constant along all the reflector tip, which is the angle between reflector tips and the bottom boundary of SDRs. So when this part is not observed, we can measure phi from here, and it's proportional, the tangent phi is proportional to TE to the power of minus 3/4. Using the three observable, we can estimate an average elastic thickness TE of 2 kilometers from this profile. And we can then use this as an input parameter to generate a elastic model profile that looked like the data. So the analytic thin plate model can reproduce general features of SDRs and explain their formation, but has several assumptions like elastic thin plate. And this assumption could introduce inaccuracy. The major one is this elastic thin assumption. So the yield strength envelope for this case looks like this, and you have the maximum extensional and compressional stress at the surface and at the bottom. However, for more realistic elastoviscoplastic EVP and thick plates, the yield strength envelope look like to the right. And when you overlap the two, you can see the difference. The red part indicate the missing strength due to brittle deformation, and the blue part indicate missing strength due to ductile flow. So overall, the bending moment a thick EVP plate can sustain would be much smaller than analytic thin elastic plate. In order to map lithospheric thickness H of L to effective elastic thickness TE, we need to quantify effects of different assumptions for between numerical lithospheric thickness H of L and analytic elastic thickness TE on plate strength and SDR geometry. To do that, we built a series numerical thick plate model with different rheology. And to say for the interest of time, I will only present one example from the M3 model with thermal evolution and density structures. So as you can see, here's the model setup. We stretch on the right with a constant rifting velocity 1 centimeter per year. And initially, upper crust are flat, and we intrude dikes into the rifting center that has a higher density that will load the surface downward and cause bending. And we fill in lava loads on top whenever the surface bends down. The numerical lithospheric thickness H of L is quantified from the surface to where differential stress is less than 5 MPa. Let's take a look at one of the model run. Initially, the upper crust is flat, and then as the denser dike load the surface down, we fill in lava, and as you can see, the flat surface is bent now. Due to the bending stress near the surface, it caused brittle deformation indicated by this plastic strain. And the bending also caused compressional stress indicated by this blue color. Because of the heat input from the dike, the rifting center has the thinnest lithosphere. And here's the viscosity structure. Eventually, we form these bent lava flows that tilted toward the rifting center. Looks like the data. And here's the results. So we have a lithospheric thickness for this model, 16 kilometer. And we measure the observable and can estimate the TE from this geometry. And we also run another 15 models with different H of L. Here is the model result summary. If it is elastic thin plate, it should be 1-to-1 relationship between TE, analytic elastic TE, and the numerical lithospheric thickness. However, due to brittle deformation, the elastic plastic thick plate model show a decrease in strength. And due to missing of ductile flow, the EVP thick plate is the weakest. We use the most sophisticated EVP thermal model to map the data onto our numerical mapping. And the Voring margin and Argentina margin show a TE from 1 to 3 kilometers that map to lithospheric thickness from about 3 to 6 kilometers. So to address the first question, we have our conclusion here. We derive 3 observables, and then that help us to estimate the elastic thickness of SDRs from 1 to 3 kilometers for the 2 margin. And then we develop a 2D thermomechanic model to map the TE to lithospheric thickness H of L to 3 to 6 kilometers. Mental potential temperature might be a major control.